Okay, so let's start our webinar. As you can see, today's webinar is on the topic PyTorch. It's going to be a very introductory webinar on PyTorch. Of course, I can't cover everything in 1 hour. No one can. Uh, but I will touch all the basics of tensors, that all the knowledge that you need for your projects. So basics of tensors, uh, then the autograd function that is used for back propagation, for computing the gradients and optimizing your neural network. And then if we have time, we will go through the whole process of how autograd is working on a sample neural network. Okay, so first of all, what is PyTorch? PyTorch is a scientific computing package, and it's targeted for people who want to use vectors, matrices, vector operation, and who want to do a large amount of vector operations. And so obviously, this large amount of vector operations are involved with deep learning, right? So when we define a neural network, what we define is a, a large vector, or a large matrix, and the matrix have their own elements, and these elements are like the weights of that neural network. So, and when we want to perform operations, computing operations on these elements of these matrices, uh, sometimes it becomes very difficult to perform these operations on a CPU, right? So that's why we use GPUs. And when there are thousands and thousands of parameters, that is the elements of these matrices, thousands, sometimes even hundreds of thousands, uh, and performing same operation on these thousands of parameters again and again for thousands of iterations can bring a huge load on your CPU. And that's why uh, people came up with using the power of GPU to perform these operations. But in order to use GPUs to perform these operations, you need to uh, convert this NumPy arrays. Instead of using these NumPy arrays, you have to use something called tensors. Now, what was the need to make these tensors if you already had an array or a NumPy array uh, in the basic Python packages? The need was that using NumPy arrays doesn't allow or doesn't facilitate to use all the power of GPU computation, uh, because what makes GPUs so fast, what makes performing operations on GPU so fast is that they use parallel computing. So if you have a large number of elements, so some elements will go on one core of the GPU, some elements will go on the other core, and some other elements on some other core, and their operations will be done in parallel instead of in NumPy array. When operations are performed in series one by one, with GPU you can perform these operations in parallel on by dividing that matrix into small parts, and then all the small parts can be computed in parallel, can be operations can be done on them in parallel, and then they can be again put together and sent back to CPU with the answers, with the output. So this is made possible only on GPUs. And to make this possible on GPUs, you can't use NumPy arrays because they can't be while computing, while sending to GPU, they can't be split into parts and then again put together and sent back. It's difficult with them. So that's why we came up with the idea. uh, People use the tensors for that. So tensors are just NumPy arrays, but they are more efficient in terms of parallel computing using GPUs. Uh, so if you want to use whole power of GPU, you better, if you have NumPy arrays, you better convert them to tensors and then uh, send them to GPU for computation, or just create tensors from scratch and then use them for this parallel computing. So the whole point of tensors and GPUs is that you want to perform large number of operations on large vectors, large number of matrices, and you want to make it more efficient. So that's why tensors and GPUs. So let's see what the basic operations that can be performed on tensors. So first of all, we have to import torch, and you have to import torch vision. Okay, now the first command uh, is is available. Torch.cuda is available. So this will check if I'm using a GPU, a GPU graphics card uh, that has CUDA on it, or I'm just using a CPU. So this will, I'm gonna run this, and it says false because I'm using a CPU. I don't have a GPU right now on my local computer. But when you perform this operation in your Udacity workspace with GPU enabled, this should give out to be true. Okay, now let's see some basic operations. So uh, A is just like a NumPy array, you create a torch.tensor with these inputs, these elements, and print, and it will give out. So this is a simple one-dimensional array. Let's call it tensor from now on. So simple one-dimensional tensor, and I just created this, and this is the output. Now I will make it more complicated. So I will make it two-dimensional tensor. So this has let's say, I think it has three columns and 4 rows, right? So it's like a matrix with 3 columns and 4 rows. So again, yeah, it's so simple to create tensors in Torch, just like NumPy. Similar operations. Let's see their shape. So it's just 3 elements. Same. It will give out same thing. With B again, it should give out 4 by 3. Hopefully, yes, it's correct. And B dot shape 0, so it will just give out 4 because it's the first element of that shape tuple. There you go. So the point of all this is that the operations are similar to NumPy array. So this is to facilitate ease, so that you don't have to learn whole new types of syntax to perform tensor operations. Now these were when I created this tensors, I didn't mention any type for them. So what if I want to create a float vector, a float tensor? So this is one way to create a float tensor, and then I'm going to print it. So again, instead of just outputting 2, 3, 4, it outputted 2.3 point. So that says that it's a float. Let's see its type. Float. Yeah, it's a function. Okay, yeah, it's a type. So this gives out the object type, not the type of not the type of the elements, not the data type. So this will give out data type. That's float. 32. Same thing again. So, yeah. So now this gives out the memory location where it is stored. Now double tensor. Double tensor is just like double in Python. So if you use float, it facilitates 7 decimal points. So precision up to 7 decimal points with float. If you use double, it's going to be 15 decimal points of precision with double. So it will just use double the I mean, I don't think it will use exactly double memory, but it will use more memory than the float, obviously. Yeah, so I declared it. Now I'm going to print it. Yeah, so it says float 64. There are other ways to, instead of saying float tensor, I could say here, when I declare it here, I could say d type as float here, and it should work. There is some other syntax for it, but it does work. If you just you can mention float here and it should work. Maybe, yeah, yeah. So either from here torch.tensor, and then I decide to call it torch.float or torch.double, or I can declare it as this way, float tensor or double tensor. Okay. So again, let's check the data type of this. It will say float 64 instead of double, because it's float. Uh, it is float 32 and this is float 64, and it's double the. It uses double the bytes to store single element, each element, as compared to just float. So let's see, let's perform some mathematical operations. So c dot mean, so it's the mean of, this will give out the mean of all elements of C. If you add them up and divide by total number of elements, that is 12, it should give out 5.5833. Again, same, instead of C mean, I use this same. Now I will take the mean of D. So again, mean of all the elements, sum and divided by number of elements, that's 12. There you go. Again, another operation is to get standard deviation. There you go. So just like the point of the first part was to just show that just like NumPy arrays have different basic operations that can be performed on them. Torch, the tensors can also be performed in the same way. Similar operations can be performed on torch tensors as well. Now, reshaping the tensors is very important, especially if you are using neural networks, because basically neural network operations are like dot products, and when you in when you where depending on your input layer, uh, you should know what the shape of your input layer should be, whether it is uh, let's say if you have an 8-dimensional vector. So in PyTorch, the input has to be 1 by 8 instead of 8 by 1. So you should know how to input this. Uh, it's either 8 by 1 or 1 by 8, but if you have an input of some weird shape like 4 by 2, you can't enter this as input as the input layer. It has to be made into a single dimension vector. So it could be either 8 by 1 or 1 by 8. So to convert these into these, you need some reshaping. You need to perform some reshaping operations. So what was our B? was 4 by 3. So let's check its dimensions. 4 by 3. Now the way you change the dimensions of your tensors is by using view. Now when you use b dot view, it won't actually change the dimensions of b. It will just show you, it will just give you a view of the change dimensions. Okay, but if you want to change its dimension, you need to do this b equals b dot view. Okay, so and just like numpy, it should be known that since b's total m by n is 12, m 4 rows 3 columns, m by n equals 12, right? So this, when you change this to a new shape, the product of rows by columns should also be the same. It shouldn't change. So if I use b dot view to 6, it will work. But if I instead I used something else, b dot view 2 by 10, it will give me an error because it should have 12 elements. It has 12 elements, so the product should be 12 always. I'm gonna delete that. Yeah, so as you saw, I did b dot view, changed the shape to 2 by 6. So it just showed me a view of the changed tensor, but it didn't change the actual tensor. The actual tensor is the same. So if I want to change the shape of the actual tensor, I need to do b equals b dot view. So it's changed, and then I'll view it, and then now it's the new. Now, the one of the best things in tensors is using -1 in the reshaping operations. So if you want to convert your tensor with 12 elements into a shape of something, comma 1, so you just want one element in the last dimension, and everything else should be uh, in the first dimension. And you're not sure, you don't know how many elements. Suppose it's a uh, very large vector with so many elements, or maybe you got b somewhere in the middle of operations. You are performing operations on some other um, tensors, and then b was one of the output, and you are not sure what this output of this tensor is, how many elements, what is the shape of this tensor, uh, right? And also you can't while writing algorithms, you can't write b dot view or show me what the b dot view is and then I will input it. You can't stop the computations in between. So to facilitate that, you can just say b dot view -1 comma 1. So I'll just this way the program, the PyTorch package will take care of reshaping the tensor. In this case, you will not you don't have to know what the exact shape of b is, and then uh, input b dot view and specific shape. So this facilitates that. So if I do b dot view -1 1, so it will keep one dimension, uh, one dimension in the second dimension, and the rest will be in the first dimension. So it should be 12 by 1. So yeah, 12 rows and just one column. You could do other way. Again, this is just view. It's the actual tensor hasn't changed. The actual tensor is 2 by 6. So I could do the other way. So this seems very simple, but many people don't know. Like when they see view and then they see -1, and then they get scared. And what is view? What is this -1? All of a sudden. So it's good to know these things. So yeah, so it gave me a 1 by 12 vector. So it put 1 in the first dimension and everything else in the end, in case I didn't know what the actual shape of B was. So this facilitates. And not just one by this, you can use any different combinations of shapes. So let's first of all, let's take at this. What this will do is the same thing as this. So here again, I knew the total elements were 12, so I could put it. But again, -1 facilitates. Using -1 facilitates this. If I use -1, 4, it's going to be 3 by 4. All right. So now, what if there are more than 2 dimensions? Right. So, and mostly in deep learning, there will be more than 2 dimensions, whether you are using image data or text data or even your state inputs. They could be of multiple dimensions for more complex environments. So let's create a random tensor. Now, I forgot to mention one thing is that the rand. Okay, I didn't use it. The rand function here. So rand n will sample the elements from a normal distribution. If I just use rand, it will sample it from a uniform distribution. Okay, so that's the basic thing. So let's create B3, print it out. So these elements have been sampled from a normal distribution. So it's a 2 by 3 by 4 tensor. So 2 of 3 of 4. So there are 2 stacks of a 3 by 4 matrix. This way you can view it. So yeah, and I'm gonna see the shape of it. This 2 by 3 by 4. Now again, this -1 is going to be very useful. So if I just use -1 by 4, it's going to be it will put 4 in the end and all these together in the first dimension. So it will make it a 2-dimensional tensor. So yeah, so it becomes 6 by 4, right? 2, 3, yeah, so 6 by 4 tensor. And you can see how those elements were put together. So I kept 4. So the innermost dimension was kept the same. So it didn't change the structure of the columns in any way. And then it put together the 2 of the 3s, right? So if you should look at it this way. So there are from the back. So there are four columns, and there are 3 of these 4s. So there are 4 columns. There are 3 of these 4 in one instance, and there are 2 of these 3 by 4. So this and this. So when I just keep when I didn't change 4, it put together these 2 of 3 rows together into 1 of 6. All right. But what if I want to change the shape in the middle somewhere? So in here, what happens then? Again, it should be noted that the product should be the same because the number of elements are the same. So if this is 24 elements here, whenever I change the view, it should keep the product to be 24. So if I use 5, the product getting the product 24 isn't possible. So this will give me an error. So now let's see this, how this works. Now I'm saying that make the simplest dimension 6 of those simplest dimension and 2 of those high level dimension, and then change the rest in between. So let's see how this stacks, and then I will explain what happened. Right, so we got 6 columns, and we said that I want 2 of something that has 6 of these. Right. So instead of going into all that complication, just say that just divide this by 24. So 12. So if you divide by 24, 2 6 are 12. So 24 by 12 is 2. So there's going to be a 2 two dimension in the middle. The second dimension is going to be 2. Just simple. Again, this should give me an error. Again, it says that invalid for input with 24 elements as expected. Yeah, so random number generations, that's what I was referring to previously. So if you just use rand, it will give out numbers, it will sample numbers between 0 to 1 with uniform distribution. And then I'm going to show it. If I use rand n, normal distribution. Rand int, so it will give out numbers between 6 and 10, five numbers between 6 and 10, and those will be integers. So let's see. Yeah, and if you see here, 5, I use 5 comma nothing. So this is a single dimension matrix, or just an array, as you can see here. Well, it's a tensor, but yeah, you can get it. So instead of saying, so if you see here 6 to 10, so numbers between 6 and 10 of the shape 3 by 4. So this will give me a tensor of 3 rows 4 columns. As compared to this is just 5 rows and 1 column. So let's perform this. Again, the important point here is that it's going to give me integer numbers. Yeah, if I want to see number of elements in R4, I just perform this operation 12. So yeah, now this seems very easy now because you know how many elements are there, but when you perform large algorithmic computations, this will be very useful to you. Again, just like numpy.zeros, it's torch.zeros of tensor 3 by 3 shape, and long. So long is also like an integer, but it has more memory in it, or it uses its range is larger than just using integer. Range of numbers it can go to is larger than just int. Once again, and default is float. By default it will be float if I don't mention anything here. So if I just remove this, it should give me float. Similar operation. Yeah. Or I can say here, I'm saying that create Z2 and make it of shape Z1. So for that, I use the like function. Again, so these are some operations, adding operations. So again, when I add two tensors, their shape should be same. So that's why I changed them here previously. Yeah. Another useful feature is using underscore. So what underscore does it does it in place. So if I do z4 dot add in place z3, so it will change the elements of z4 such that the new z4 is the output of z4 plus z3. So it will do it in place. That's what underscore means here. Again, slicing operations similar to NumPy. Yeah, you can see here all rows and just second column. This is all rows and columns from 2 to 3, rows from 2 to 3, and columns from 3 to 4. So similar, same, just like NumPy. Okay, so in the end, I'll leave you with this. So 100 plus tensor operations transposing, indexing, slicing, and many operations can be found on the PyTorch website. 100 plus tensor operations. Just beyond just these basic ones. Uh, if you need to refer something, if you're stuck something, and if there is a error giving some problems with your shape of your tensor or something with your tensor, you can go to PyTorch website and search for that, and yeah, and it will help you. Now let's move to the autograd function, the grad function that you saw so many times in your DQN programming coding example. I'm here in DQN now. Yeah, and then you saw something like this. What is this? Torch no grad, right? And then again you saw some zero grad. There was zero grad. What is this zero grad, and what are these steps? What does backward do? So we will go into some brief introduction, brief information about that. So I'm into a new notebook now. So if you need more information about AutoGrad, again you can go to this PyTorch link. So this notebook, I got this notebook from this PyTorch tutorial website, PyTorch official website, and so if you go to this link, it will bring you here. 60-minute bleeds, and then there's all information. So what is PyTorch? So this will have all the basic tensor operations. If you click on this, it will take you to the AutoGrad basics, information about the AutoGrad function, neural networks, then the basic, some simple uh, model for training a classifier. And then if you want, you can take a look at the data parallelism optional. Okay. So this notebook, I got this notebook by going here and then download notebook. So if you want, you can do that as well. You just have to go to this link or just put PyTorch, go to PyTorch website tutorials, and there should be all these links for all these links available there. So yeah, so what is AutoGrad? So AutoGrad is a package that facilitates automatic differentiations for all operations on tensors. So why do we need automatic differentiation in the first place? So when we covered the neural network webinar, I said that you compute the total output y, and then you compute the loss, and then you have to compute the gradient of each of the weights with respect to the loss. So how does the loss change as you change the value of weights? So that's the gradient that you have to compute. To compute those gradients, AutoGrad helps. AutoGrad package makes it very easy. And then, so that's the whole process of backpropagation, that you will try to reduce the loss by changing your gradient, right? And then change your gradients, and then again run, again compute loss, again change the gradient, the whole thing. So for computing different gradients for automatic differentiation, you use this AutoGrad package. So let's take a look at some useful functions in this AutoGrad package. So first of all, torch.tensor is the central class of this package, and then this class includes some methods and attributes. So first of all, there's the attribute called requires grad. So if you create a tensor and set its attribute as a requires grad. So I said if you create a tensor, because requires grad is an attribute of torch.tensor. So when you create a tensor, you create an instance of this class, right? And then all those attributes and functions are available with that tensor. So if you set the attribute of your tensor requires grad as true, PyTorch will track all the operations done on it. So if you create a tensor x, which is a, and then there is a, you perform some operations on x and then you create y. So y is function of x. So requires grad, setting requires grad equals true will track all those operations done on x that lead to y, and maybe operations are done on y later which will lead to some other tensor z. So required grad equals true, as true will keep track of all those operations done on basic x, so that it will be used later to differentiate with respect to y or with respect to z, or if you're getting that picture that about the loss function, right? So requires grad equals true is set as true, and when you finish all your computations, you can call the backward method, and then it will compute the gradients automatically for you. So it's just like computing the loss function. um, right, you have your parameters. Those parameters are tensors. You set requires grad equals true, and then you perform functions operations on it. So linear function, and then ReLU, and then linear function, then ReLU. You get y, then you use y to compute loss, and then you have to differentiate loss with respect to your basic weight. So that's all that can be done automatically with all the differentiation can be done using this backward method of the class tensor. Okay. Yeah. And the gradients for this tensor will accumulate in the dot grad attribute. So we'll go through this one by one in the next section. Now, to stop a tensor from tracking its operations, all the operations done on the tensor, you can use detach. So this is the opposite of requires grad equals true. You can do detach, and its operations, the operations done on the tensor won't be tracked anymore, and the it won't be used for computing gradient anymore. Another way to prevent the tracking history is to use torch.nograd. So when you saw in DQN, so I'm in this DQN notebook sample code, and here I'm in this agent class, and here we had a select act or taking action, a method that took action, and we used your network to generate action values given state, right? So over here we use this torch.nograd. So what torch.nograd does is same thing. It stops uh, the tracking the operations of the gradient, right? So as you can see here, we are just evaluating. We use eval because we are not training. We are just evaluating the network. So the parameters of this network, I don't want them to change. I don't want their operations. This operation, I don't want this operation to be tracked, right? I'm just evaluating this, so that I don't compute wrong gradients. I just want to skip these operations from being tracked in that autograd function. So that's why I used with torch.nograd. Again, I'll go back to this autograd tutorial, and yeah, so I use this. This can be helpful when evaluating a model when required grad is true. So you said required grad is true for all parameters, but I want to skip just that one operation. So I put that operation in this block, which with torch.nograd. So it will, so the autograd function will ignore that operation in computing, while computing gradients. Okay, function. Yeah, and so the function, the grad function is where all the functions performed on that basic tensors are stored. all the history of all the functions performed on the tensor are stored. That's grad fn. This is another attribute. So let's take a look at this autograd, how it's used. So let's import torch. Let's create this x. So this is going to be our basic tensor, and see, we have set requires grad equals true. So from now on, any operation performed on x will be tracked, so it will be used later to compute gradient. So let's create this. Now I'm creating y from x. So y is a function of x. So um, my autograd function is going to take a note of this and store this. Right. So now y was created as a result of an operation. So it has a grad function because y is a function of x, right? So it won't show it, but it has a grad function which is a function of a tensor. So that's why it's stored in y. Now we perform more operations on y. So we are creating z from y, and y is created in turn from x. So let's keep track of this operation. So we create z from y, and then we create out from z by taking main of z. Right. So this is printing out z and out for you, and both have grad function because they were made from another tensor. They were made from another tensor. So the grad function keeps track of how they were made. So you can see grad fn is mean here because it was created with the main operation, and here it's mul backward because it was created from a multiplication operation. Z was created, so it keep track of how it was made. So yeah, as we saw previously, this underscore, we put underscore after a function, so that means in place. So requires grad underscore changes an existing tensor's required grad flag in place, and default is false obviously because here we called it as true. Previously, when we just saw the tensor operations, we didn't write anything here, so the default was taken as false over there in the other notebook that we saw about tensors. Yeah. So there is a 2 by 2 perform operations on it, and now this will show if a dot requires grad is true or false. Uh, Now, since the default is false, this should be false. Now, what they are doing is they will change it in place to true, and then again they will print it, so it will show true second time. And uh, then b is made, and then b's grad function will see, and then it won't have this previous operation. It will only have this latest operation in its grad function. So yeah, so first was false by default. Second was changed in place to true. So if you want a tensor to not note any functions now, but later, so you can just change it later in place. A dot requires grad true in your algorithm. So you can use this. And B, it only takes sum here, or sum of the product of A, right? Sum is the basic operation here. Instead of this operation, it doesn't note this operation, obviously, because it was false here. Right. So now how do we compute gradients? So you use the backward function. So when I use out dot backward, now out is made of z here. Yeah, mean of z. So if I use out dot backward, and then I will print x dot grad. So x dot grad would be now when I do out dot backward, it will perform gradients with respect to all the variables of out. So with respect, so d out by dz, then d out by dy, and then d out by dx. So now if I just want to see d out by dx, I will use x dot grad. as 4.5. The computation is given here. It's pretty straightforward. Then they are saying that what the gradient backward operation, what it does, it basically uses this Jacobian function of computing gradients. That's what some more information on it. Right. Yeah. So again, it's the same Jacobian. Uh, yeah. Yeah. So what was important until now is what are the main useful attributes of the torch.tensor function. Autograd is a package which provides this functionality. So torch.tensor is the class. It has attributes this backward. Then you detach. You can use torch.nograd in the block to avoid a particular operation, or you can do a requires grad equals to in place. Right. If you want A to not um, record in history at first, and then later on you want it to record the history, it will only record the later ones with this in place equals. And then with out.backward, out.backward will compute gradients, differentiation of out with respect to all its elements, z, y, x, and then you can print out individual gradients here. All right. So that was the basics of some basics of tensors, some basic operations, and the autograd function that you can perform. There are more tutorials on that Python website uh, where they now there is a tutorial on Udacity website about fashion MNIST, how they are classifying the images from fashion MNIST. That is a useful one. You can go through that to practice using this autograd functions and the attribute of autograd, uh, the packages, the attributes of this class, backward and everything. So that's a good practice for you. Here there is this neural network tutorial again on the PyTorch website, and here they show how to use this on neural networks. But you have already done this in the DQN coding example. So instead of going through this, I would rather go through the DQN coding example and see wherever grad autograd is used. Now you will know what the use of this was. Right, this was just to evaluate. I just want to evaluate, so don't record this. Then when I have this learn method, I first now self optimizer.zero grad will set all the gradient values to 0 so that I don't start with any random initial values. So all the gradient values are set to 0. Then you perform this differentiation of loss with respect to all its components. Right, and then this optimizer.step is doing one step of optimization. Right. So yeah, so that's it for this tutorial. I didn't know it will take 1 hour for simple two notebooks, but we learned the basic tensor operations, and you can check out more tensor operations here. You can refer them here. And autograd function, very important and very powerful function provided by PyTorch to compute gradients. Again, if you have any questions, please reach out to me on Slack by direct message about anything, including the navigation project, and I will get back to you as soon as possible. Usually, my response time is very quick. Within a few minutes, I get back to people. So please reach out to me. And now I will end this webinar. So thank you.